So thank you for attending this presentation. Not quite as early as Stuart's presentation earlier. Actually, curiously, how many people were in Stuart's presentation earlier today? So, okay, quite a few. So we can compare notes afterwards. Okay. So there's the obligatory legal statement. So what am I going to talk about today? So I'm going to do a bit of a recap on the unmodifiable collections in the JDK, just to say what we have there at the moment. I'm going to give a brief overview of immutable collections in external Java libraries and JVM-based platforms. And then I'm going to talk about immutable collections leveraging persistent data structures. So when I refer to persistence, I do not mean database in any way whatsoever, or persisting to non-volatile memory, or any of those things. It's a very confusing term, but persistence is sometimes easier to understand than immutable when people hear mutable and immutable, and they can't differentiate between the two, so sometimes people refer to these as persistent collections rather than immutable collections. So when I refer to these immutable collections, I'm making no claims whatsoever as to the immutability of the collection's elements. So I'm not talking about immutability in the large, in the language, or forcing immutability all the way down deeply into these structures. I'm just talking about the collection structures themselves. This is a huge bike shed area. You can talk about this for months and months and months and months. So I'm just trying to sort of enclose the scope in just the collections for this talk. So there is a huge set of advantages to being immutable. I think the first that occurs to me is, if I don't have to think about data races, I'm a happy person. If I have to think about data races, I get a headache. If you're dealing with concurrent stuff, and you know that what you're dealing with is immutable, you can safely trust that, and you can understand that, and that's a lot clearer than having to deal with sometimes with data races and the headaches and debugging that actually comes with it, and that's a huge advantage. It's also, if you have things that are immutable and are trusted to be immutable, you know that nothing else can scratch from them, either on purpose, maliciously, or by accident, and that's a nice property as well. So if a library that you're using uses these data structures, you know you can trust this library. And they have a bunch of properties in terms of optimization. They're effectively constant. So that gives a lot of opportunities for the Java runtime, hotspot, to optimize these things and treat them as constants and inline them or constant fold them when generating, when hotspot generates little bits of code that are optimized. And they also have properties that you can optimize these things in the Java implementations over space and time. If you have a small collection, you can choose to use a different data structure than if you have a large collection. And Stuart Marks did some of these kinds of optimizations for his collections, list.of, set.of, map.of. For smaller collections, they're more optimized, they save space, they trade off some space versus time. And you can do these types of tricks when you have immutability in your collections. So this is my wish list for immutable collections. If I were going to do this in the JDK, this is no commitment to doing this in the JDK, but if I were going to do it, this would be my wish list here. So I think the first one to me is, if you're coding using immutable collections, I'd like to see that in the type name. I'd like to see that in the API. So when I read the code, I know, this thing is immutable. I have to treat it differently to, say, list or map. If it was a mutable list or a mutable map, I can treat that differently. I know it has a different API. I know I have to consider this slightly differently than the way I use my algorithms or the way I develop my algorithms. Incidentally, has anyone programmed in Clojure at all? A few? It's kind of mind-bending because it is totally immutable for the most part, and it's kind of mind-bending at first if you're used to the mutable way, not immutable, mutable way of coding. Your algorithms tend to change. And I think it's worth actually experimenting with languages like Clojure and Haskell to see how you can code in immutable ways rather than mutable ways. It really changes the way you think sometimes. These collections, I think, should be sealed. And what I mean by that is only trusted parties can actually extend these collections. So I wouldn't want to let anyone else extend my immutable list because I don't trust them. I don't trust them to do it properly. I don't trust them either because they're being a black hat or a white hat in terms of what their motives are, or because they've made mistakes. We've had this with our own collections in the JDK. They're open, and we have to write defensive code against incorrect collections, people who've extended array list, people who've extended hash map, and so forth like that. They don't necessarily do the right thing. I want these to be closed, and only we can implement them, and then we can guarantee the immutability of these things. I would like them to provide a bridge to the mutable collections. So you have to opt in and say to list or to mutable list, rather than extending from list. If you extend from list, then you can easily pass it around to something that accepts list, and it just becomes into the old collections, mutable collections world, where you might operate on it and do a mutating operation, get an exception. I don't want that. I want explicitly something in the code that says to mutable list or something like that, so you really know when you're transitioning from the immutable to the mutable world. And I want efficient construction, updates, and copying. So if I have an immutable list, and I add an element to it, I want a new immutable list, but somehow underneath it shares a bit of structure between the previous collection and the new collection, so we can save some space, maybe trade off some time and save some space, but we get structural sharing underneath, and we can do efficient forms of copying. I want a way to build these collections up in a confined, mutable way, and then go freeze and say, now you're immutable. I may, if I get time, show you some stuff what we're doing there on that. So that's my wish list. I guess you could describe them as goals if we formalize them a bit more. So what have we got in the JDK? So the JDK has a notion of unmodifiable collections. Everyone know what they are? You've used these things before. So unmodifiable is a runtime property of a collection. So if you have an unmodifiable collection, the modifying methods like add, put, remove, throw unsupported operation exception. And there's no way to directly query this. And you might ask, why would you want to directly query it? Well, you might want to know if you need to make a copy or not. If you've got a list, how do you know it's unmodifiable? Well, you could do an instance of and look at some internal JDK collections, but I wouldn't recommend that. So if we wanted to add an efficient copy method to the JDK, we can't actually do this and let third parties opt in if they're going to opt into their unmodifiable view as well, for example, Guava, which I'll get onto in a moment. So an unmodifiable view or wrapper is essentially a source to a backing collection. So you've all done this collections.unmodifiable list source list. So if the source list is modified, it will be reflected in your wrapper as well. So they're not really immutable things in this notion here. It's just what you get back is an unmodifiable view over your source. And you can have directly unmodifiable as well with the list.of. So if there's no source here that you can observe or see, you're just creating a collection, kind of like a collection literal in the language, and you're getting back an unmodifiable list back. So how do you get immutability with these things? Well, usually what you do is you do the unmodifiable list, you clone it, because you don't know whether the source is unmodifiable or not. You have to take a clone, a copy, and then you wrap it, and then you throw away the source. I don't want a reference to that because I don't want to know what that is. I don't want to modify that at all. Another way to do that is using stream. So you can use collecting then to list, and then wrap it in a list there. And I'm throwing away the source implicitly here, so it's not going to be referenced from outside anymore. And of course, list of and friends are as if the source is never accessible. So that's the way I kind of describe unmodifiable collections to myself. And you have to jump through hoops if you want to get something that's immutable and you know is immutable, but is not reflected in the type system and so forth like that. So if I go back to my wish list and look at the JDK collections, they're not doing very well here. There's no types to indicate that you've got an immutable thing. It's not sealed. You can open it up. Tautologically, it provides a bridge to itself. And there's not really any efficient construction, updates, and copying. If you get a list and you want to make sure that no one scribbles on it, you have to take a copy. And then if you want to make sure no one else scribbles on it, when you return it, you either make a copy or you wrap it and hold the source to yourself tightly so no one else can get it. So I think unmodifiable is a reasonable abstraction for mutable collections. but it's not really good for immutable. Sorry, did I say mutable or immutable? I'm getting mixed up. It's a good abstraction for mutable collections, but not for immutable collections. There, that would be my argument. It doesn't mean we shouldn't improve this notion in the JDK, but I think if we want to get to truly immutable collections, we have to have something else. So what does Guava's immutable collections do? Anyone use Guava's collections? They're really quite popular, very well designed. So Guava has a bunch of sealed types, such as immutable list and immutable map, and these implement the corresponding JDK mutable collection type. So mutable list implements list. And copying is kind of smart. It knows the copy of, if it takes the other collection, and it will know whether it's an immutable list of its own kind or not, and decide to return it back or do a copy. So in some sense, it's kind of smart. Whereas when we're doing the unmodifiable case, or when we're in the JDK without these things, we have to program defensively and take copies. So I'd say that manifests immutability, it's sealed. It doesn't provide a bridge, so you don't opt in explicitly in source. Because it extends list, you can pass it around to something that accepts list. I don't like that. I'd prefer explicit opt-in to know you're transitioning between the two. So it's sort of, as soon as you pop up to list, you're in the unmodifiable world again. And it kind of provides efficient copying, a bit of efficient construction through builders, but it's not what I like. They're a good compromise. They have some good properties with them, but to me it doesn't go far enough. There's Eclipse collections. How many of you used these? These are previously Goldman Sachs collections. This is, I describe as something for everyone. It's quite a cornucopia of various collections out there, and you may find something very useful in these types of collections. From what I've looked at here, I'm not an expert on these collections. They manifest immutability. They are not sealed. They do provide a bridge, as far as I can tell, and they have similar issues as Guava does in terms of efficient construction updates and copying. So if I look at vavr, previously called Java slang, people heard about that? Nice functional library. Clojure, Scala, maybe Kotlin too, but I'm not as familiar with Kotlin. I think these tick all the boxes, all the goals or wish list that I have. They manifest immutability, they're sealed, they provide a bridge, and they also provide efficient construction updates and copying. Now, I haven't verified this fully, but that's my gut feeling here and what these provide. So let's look a bit closely at the efficient updates. So what is going on here? All these collections, some of these collections, these libraries or platforms provide, leverage something called persistent data structures, predominantly for map sets and vectors. Vectors are non-linked lists. They're not Java util vector, which should be deprecated, but possibly never removed. Is it deprecated already, Stuart? No, not yet. Same for hash table as well. So they leverage something called we call persistent data structures. So what is a persistent data structure? So a persistent data structure is something that preserves a previous version of itself when modified. Now you could easily write your own persistent data structure by doing a copy on write. That would be terribly inefficient, and that's what we have to do today to code defensively in the JDK. But what these persistent data structures do, they all have a common theme underneath, and that's called hash array mapped tries, or HAMTs for short. And they are the basis of efficient, persistent, immutable map sets and vectors. So I think these were pioneered in part by Phil Bagwell, who worked in Scala and worked at TypeSafe and I think Lightbend. Unfortunately, he's passed away now, but I think he pioneered some of these implementations and designs in Scala, first of all. What's good about these is these allow you to provide structural sharing between the new and previous version of a collection. So instead of taking a whole copy of something, you take a copy of only the bits that you need to change, and then you can share the other bits. And because it's immutable, you know that those other bits aren't going to get modified. They are effectively constant time, a bit of wiggle room here for many operations, and they can be cache friendly as well. So if you're traversing over them, you're often prefetching stuff from the cache, and so you get good performance. They won't beat something like array list. Array list is damn hard to beat. But they trade off some performance for some structural sharing. So what's the basis of this? If you know what a tri-tree is, I copied this from Wikipedia. So you can go to the Wikipedia page instead if you want to. So this is an example of a tri-tree. So a tri-tree, basically, it stores a bit of the keys. If you're making a map, it stores a bit of the keys in each node as you go down. So if in the example here, you've got a trie for keys A, 2, T, TED, 10, I, in, and then numbers for the values. So you basically traverse the tree saying, oh, T, okay, I go to this node, and O, I go to 2, and so forth like that. And you only need to store a prefix of your keys in your tree for all of the entries that you actually have. So it's it can be quite an efficient mechanism and data structure. And often these kinds of data structures are used when you're typing something in and you do word completion. You might be using a trie underneath to select the possible words that you might want to complete against. So essentially a trie here, you have an alphabet. Here we have the alphabet A to Z, lower and uppercase. And you have a string, and this string in this case would be unbounded because it would just be a word. But we can use the same techniques in hash array map tries. So a hash array map trie is essentially a symbol instead of a letter of the alphabet. You can say it's a symbol of a 5-bit sequence. It's just a number from 0 to 31. And you can say the string is fixed in size of length 32 bits consisting of 7 symbols. And just the last symbol is just truncated to 2 bits. So the string in a hash array map trie is essentially the hash code of an object, which is the key. So we're sort of laterally transforming our domain to a 32-bit string and chopping it up into a little bit of symbols. And that's the sort of our symbols are our alphabet, and our string is of fixed length size. And here's an example here. So say we had a hash code of Cafe Baby here. And so our symbols would be going from right to left. Symbol 1 would be the first 5 bits. Symbol 2 will be the next 5 bits, and so forth and so on down. So we have maximum of 7 symbols, essentially a tree depth of 6. Does that make sense? All you're doing is taking 5 bits off each of the hash code. So essentially, we have a wide branching factor here. So each node in our tree, instead of, if we go back here, in our tree, each node would have a branching factor of 32, and you go down for a depth of 6. So the depth is actually controlled. You're not going to go down like depth of 64 or 32. It's pretty constrained. And it's effectively constant time to look at. What I mean by effectively constant time, if you're going to do a lookup of a key and a value, is essentially log 2 n over 5, which is almost 0.1, you can say for most cases. So these things provide good structural sharing. I will show later on, I'll show some visualization of this structural sharing to get this across more, I hope. But because of this, they're good for updates. They're also potentially good for merging and splitting. So in our collection, in our streams, when we do a parallel collection, say 2-list or 2-map, potentially we could use these structures underneath to do more efficient merging than we currently do today, because it's actually a little bit inefficient what we do when we do collect 2-list in parallel or grouping by. And these structures could be very interesting in terms of allowing you to collect in parallel and then merge them efficiently together, because we know some structures are different in each part and some structures are shared, and we can do a little bit of merging just on the shared bits. They provide good memory usage as well, which I hope to explain, and good, as I said, good cache coherency. And this is the basis for vectors that Rich Hickey coded in Clojure, and where Phil Bagwell also extended his research to look at relaxed radix balance trees for vectors. And it can also be used for multi-maps at JVMLS this year. A presenter talked about how he could use these structures for multi-maps as well, so they're quite versatile. And they can also be applied to mutable collections as well, and this is what interests me for efficient building of something before you turn it into something immutable. And I think they can be efficiently implemented in Java. They can be efficiently implemented in Scala. They're actually Java, I believe in Clojure, they're actually Java implementations. And vavr is another example of these collections as well being implemented. So here's a real naive implementation of how you might go about this. Say pmap is a persistent map. So I have a 32-way branching factor, and I'll have a key value. I need to store my keys and values as entries. So what I'm doing is I've got a node here, object array, and I'm storing 64. It's a length of 64, key value, key value, key value, key value. And some of these entries might be null, because the value, there might not be an entry actually there, and there might be a sublayer there. So if I look at the get method here for finding a value for a given key, I want to ask, what is my symbol at my current depth? So remember the symbols of the 5 bits going across the hash code here. So I've got to say, well, how do I index into that array of nodes? Well, first of all, I've got to get my symbol for my hash code. And essentially, the method symbol at depth is there. All it does is shift down by the depth times 5 and chop off and get the first 5 bits. That's it, and that's my index into my array. I look it up, I see if it's a sublayer node, I traverse down otherwise, I see if it's present, and I return an optional. Say whether it's present or not. Now that's pretty simple, but that's like 64 entries. I might not have all 64 entries in there. That's a pretty inefficient representation there. So you can do something better. And what you can do is you can use a bitmap to express which entries are present at my level in my tree. And I can have a number, an array, an object array of nodes that is of length of the number of bits set in my bitmap. So that's a more compressed representation, and that's a technique that all these persistent collection implementations use. So if you look at this implementation, you'd have the same symbol at depth as before. You'd check if the bit is set or not, and if it's not set, then you turn optional empty, it's not present. But then you have an operation which says, how do I index into this array? But all you do is you essentially chop off the bitmap for all the bits before the symbol you're interested in and count the number of bits using bit count, and then there's your index into your array. Quite nice. And the reason why this can be implemented efficiently in Java is because integer bit count is an intrinsic. And that compiles down to a pop count instruction on x86. And before that was intrinsified in the JDK, these collections were a lot slower because they had to do a lot of bit twiddling going on. I'll get to this point later on, hopefully. There's a lot more we can do to optimize these things. So I think this is a better representation. As I said, the space is required only for present nodes using a bitmap, and that's made possible with hotspot optimizations. There's further refinements you can do here and trade-offs. Subnodes and entries could be separated for more cache-friendly traversal. Steindorfer talked about this in his CHAMP work. And hash codes could be cached as well. I wasn't caching hash codes here. There's all sorts of trade-offs and experiments we can try. And the API is slightly different. So if I have a persistent map API, I might have a familiar for each. I might have a get that returns null or optional. It's up to you. But the put method, instead of returning the previous value or null, it has to return a new map because I'm not modifying the existing map. I'm returning a new map with the same things as the previous one, but the new entry inside it. And the same for remove in terms of removing something. So the API is actually slightly different here to what you might get with a hash map. So although there's modifying methods return a new collection, the implementation will actually share structure underneath. And to do this efficiently when we're building, we need mutable builders to construct in a confined manner. So what we want is when you're building something up, you want to confine this to a closure or a thread so it doesn't escape out. And then when you're done, you construct and freeze, and you've got an immutable thing. And Clojure has this notion of building. I'm not sure about Scala. It may well do as well. So I'm going to show some demos now. Now let's see how successful this will be. Actually, before I go in, does anybody have any quick questions on the explanations? No? All good? Okay. So I'm going to wing it a bit here. Let's see how this goes. So first of all, I'm going to run JShell. Let's start this up. Okay, this is actually JShell running Java 10 or 18.3, as we like to call it nowadays. I'm not going to get into discussion on version numbers. So we can use var. So there's a GitHub project here I sent a link to. This is all online on GitHub. You can check this out and play with it yourself and get an idea of how these structures work. What I've written is buggy. It's not performant, but it's functional enough to experiment with. So if you find any bugs in it, send me a push request or a pull request, and I will accept it and fix things. It's in the OpenJDK, same license as OpenJDK. So if I just create a very simple map like so, var m equals pmap of, like that, I can visualize this like so. What that's going to do, it's going to look at the structure, it's going to create a dot file, convert the dot file to SVG, and load it up in the browser. If I can get my... Okay, so here we go. This is our first visualization of a map. It's not very interesting, but it's useful to explain what's going on. So I have one entry in my map. I have a key of 1 and a value of 1. I have one node at the top here with a bitmap that says of 32 values. So this is my bitmap I showed earlier, the int bitmap, and it's essentially got one bit set, a size of 1, and there's a prefix here for 1. The key is 1. Any integer value under 2 to the 16 is actually, the hash code is itself. Essentially, that's what you need to know here. So the hash code of 1 is 1. And so I have a prefix here, the first 5 bits of 1, and the total hash is this, going from least significant bit to most significant bit here. So does that make sense? So I can add some more here. So I can visualize two things instead. So we can put another value here, like so. And we can visualize two things. So now we get the previous map and the new map, like so. So we still have one node depth. We have the previous map with a key of 1 to 1, and we have a new map with 1 and 1 and 2 and 2. So that's immutable. There's no structural sharing here because we're at the same depth here. We essentially got the two arrays can't be shared. So we have to structurally share when we go down in terms of nodes. But you can see here the prefix here is different. The hash is different, so forth like that. So it's very easy to visualize and play around with these things. So I can show a few more complex examples here. Okay, so here is a good example of what I wrote. Can you all see that? Shall I zoom in? Here's an example of building up a persistent map. And this is a common thing you might do in at least JDK code. You might have the symbols for your primitive types in bytecode, B, D, F, I, and so forth, mapping to the box types. And that you might create a map for that. So what I'm doing here is I'm creating an empty map that I'm putting my first entry in, my second entry, third entry, fourth entry, all immutably. So I'm creating all these structures and throwing them away, creating all these structures until I get the one I want. That's not the particularly efficient way of doing it, but we can visualize this and see what happens. So I'll just run this test here. And it should do the same thing as before. Okay, so this is getting harder to see. Can you see that? Not really. But the point being is that there's no collisions here, there's no subnodes. It all maps at one level deep here. And we can see the various prefixes and hash codes here. And we can see the top node here is there's 9 entries and there's 9 bits set in my bitmap, like that. And there's no conflicting prefixes here, so we're not going down any level deep. So that's actually quite a nice property. I just packed in essentially 18 entries in my object array. No spare space. If you're using a hash map, you probably you'd have to have a hash table, a bucket size of about 32 to stop the collisions. So you're already saving some space here. And it's all nicely cache coherent because it's all in a single array. So when I traverse that, I'm going to get the prefetching working as well. The only thing I don't have in here is I'm not caching the hash codes. So I'm going to take a hit in terms of time when I compare my hash codes. But there's ways to cache those too. So that's an example there. Let me show you the concept of building instead. So I showed it building structurally, immutably, and I'm throwing away arrays every time I do a put here as I create a new one. So creating some garbage collection here. But I can do the same instead by saying pmap of, and instead I get essentially what I call a builder, a pmap builder here. And all pmap builder does is has a put method on it. All I can do is add stuff to the map. And I'm doing it in a closure here, and I want to confine this builder so it only operates within this closure and within the same thread. If I operate it in another thread, it will throw a legal state exception. If I somehow cache it outside the closure by storing it in an array or in a field or something like that and operate on it when I'm outside the closure, it will throw a legal state exception. So I've nicely confined this thing. And then I can mutably update this safely because I know no threads will churn on it. And I know that if it leaks out, nothing will happen, bad will happen to it afterwards. And this is quite a powerful concept. We did the same thing with the Stackwalker API. If you've ever used this to get stacks and traversing the frames using the Stream API in a closure, in a confined way, using closure like this. And I think this is a very interesting pattern because I can build up something mutably and not throw away and create a bunch of garbage. And once the closure finishes, I freeze the collection and it becomes immutable again. I'm doing some interesting tricks with JD Sunmisk unsafe here, if you want to look at the code. I'm actually, rather than doing a copy of the data, I'm transforming the class header from something that I can write on in terms of fields to something that is the same structure with final fields later on, if you want to look at the code. You shouldn't be doing this at home, but these are the kind of tricks we can do in the JDK. And as long as we can test it and we trust our code, we can do these types of tricks. And no one else can do these types of tricks outside. That's an advantage to us, and that's one reason why these things are of interest to me, is we can optimize the heck out of these things. Anyone can write these things on top of a JDK at reasonable efficiency. I think we can do a better job in the JDK itself. So that's one advantage. So I showed that. We can just run that too, just to show that it will build a map. Like so. Okay, same thing as before. It's no different. We get the same structure out, immutable structure there. Okay, let's show something more complex. Let's show this one here. So I'm not building efficiently here, but I'm just creating a bunch of entries of fruit to color like this. And I'm going to visualize the map I built, but I'm also going to visualize the one with the blueberry entry removed. Let's see what happens there. So this is going to create quite a big map here. So if we just, yep, it's quite big. But if you notice here, we're getting some structural sharing between the two maps because we've got a subnode that conflicts on the first 5-bit prefix. So the first 5-bit prefix here, both banana and plum share the first 5-bit prefix of 00000. So we can structurally share that between the two maps that we modified. So this map will have, so it has blueberry in, but there's only one blueberry here, but it's not in the other map. We removed it, but we can structurally share this subnode layer here. So when you've got more complex layers, there's more structural sharing you can actually do here. And this is interesting. It makes it easier to split because there's a natural split point both in the array and this one here too. So hopefully that gets it across a little bit here. We can see that the prefix here, we now have two 5 bits here. The first 5 bits and the second 5 bits are two symbols. And we can see that it's always a prefix of the total hash code here when you're comparing these values. So we can do something more complex. So let's see. So here's system properties. So system properties is essentially it's a map of all the system properties in the JDK. So let's visualize this and see what this looks like. This will be a more complex one. Okay. So you get an idea of the structure here. There's more subnodes happening here. Let's scroll all the way down here. So we see a prefix here, shared prefix and other symbols down and so forth, but it only gets down to about a depth of 2, maybe 3 at the end here. So it's still quite shallow. So if you're going to look up something, it's going to traverse a little bit, but it's not going to traverse too deeply, and that's why it's almost constant time, what you're doing. So there's a good structural sharing here and reasonable efficiency in terms of access. You're probably not going to be a well-sized hash map here, but I'd argue that potentially a hash map will take up more memory. So you're potentially trading off space and time here a little bit, but they're actually a good compromise. I don't think if you're using these things, most people won't notice or won't need the extra performance. That's my theory anyway. I don't know if it's entirely true. We'd have to verify that. We'd have to do good performance tests on these things too. But they, just to express, they're showing a good set of properties here. We can look at some more degenerate cases here. So what happens if you have a collision? So 2 hash codes, two entries, 2 keys share the same hash code. What do you do then? So I have in here an int key, which essentially sets the hash code of these 2 things to 0. So I have an int key whose key is 1 and an int key whose key is 2, but their hash codes are the same. I'm just concocting this there with 1 and 2. So in this case, we have a collision here, signified by a red box. So what do we do when we have a collision? We could use a linked list. We could use a red-black tree, like we do in HashMap today. Or we could change the hash algorithm and go and use the same Hamty structure with a different hash code algorithm too, and go down. There's lots of options we can experiment with. So let's look at a degenerate case of how deep we can go down in the tree. So what I'm doing here is I'm concocting integers that just so happen, if I know the hash code algorithm internally, to create the actual hash code values I'm using in my map. So I'm creating, I want to set the 2 top level bits. Remember, it's 6 symbols with the two top level bits, most significant bits only at the end. I'm setting their values. I'm also setting their values here because the hash code is slightly shifted a bit. So the way I calculate the hash code is the way you do it in HashMap. You shift the hash code by 60 and XOR it with itself. So I want to cancel out the 1s and just have the hash code to the top 2 significant bits here, just to show the degenerate case. And so what happens here, we get 1, 2, 3, 4, 5, depth of 6, when we get our 4 values right down at the bottom. So if you're traversing this structure, you have to go down all the way down, not very cache coherent, not particularly very efficient, but you're bounded by a level of 6 deep. You're not going to go further and further. So if you're writing algorithms for this and you don't want to use recursion, you can allocate a stack on a heap of just 6. It's very nice property, that. And then we see the values in there. So that's the worst case you can possibly get, which I'd argue is not going to be very common. Okay, I think that's it. If you want to check out the code and have some fun with this or send me fixes and that, I'd be very interested on that stuff. Okay. So, to summarize, so I think unmodifiable is a reasonable abstraction for mutable, but not immutable. I hope I persuaded you of that. And for efficient immutable collections, we need persistent collections. That's what I'm arguing. Guava gets you so far. It's reasonable, but I think we could do better. And other languages and platforms actually do better. And sets, maps, vectors using Hamties have been proven to be effective in these libraries and platforms, I think. So they've proven their worth. So what about Java? This is where it becomes a bit speculative and more my opinion. I think we'll definitely continue to improve on unmodifiable in the JDK, and Stuart Marks is already working on some stuff like this. He's already got one thing in review on core libsdev and OpenJDK, and there's some other stuff in the pipe to make some good improvements here. But what about, say, selective sedimentation? I love that word. That's a Mark Reinhold word that he uses, that we have the luxury to look outside there of other languages and platforms and see what they're doing, stand back, ponder them, and take the best bits from each. Could we do that with persistent collections in the Java platform? Perhaps we could. I claim, I say it's possible to optimize these collections very, very aggressively with internal APIs, hotspot, and safely contained unsafe mechanisms that I talked about when I was doing building. There are ways that we could leverage more intrinsics. I showed you about pop count. At the JVMLS talk by Steindorfer, he talked about multi-maps, and he was using AVX style instructions to do bit manipulation of these multi-maps to make them efficient as well. There's stuff we can do there too. There's a lot of research here, but my claim is that we can optimize these things like no one else on top of the JDK can optimize today. And that is the end of my presentation. And there's some references at the back here. I'll upload this presentation and tweet about it. There's some references to some of the papers that write about these data structures. I especially like to recommend Steindorfer's thesis. I think he's done some interesting work building on Van Bagwell. And if you're interested, look at Clojure's vector. Look at the stuff in Scala, the implementations of the RBB vectors as well. And there's an interesting one at the end. It's using these hash array map tries for concurrent collections. And there's by Prokopek, very interesting, leveraging these things for concurrent collections which have similar characteristics to concurrent skip lists. Okay, I think I'm done. Any questions? No questions. You all understood that, right? Okay, thank you.